Where are we? Can I get to my hover cam? There we are. So this unit is unit 3. And I made these notes a long time ago, so look how cute they are. You can't tell me they're not cute. Okay, so on Friday or Wednesday when we last met, we were going over the polyatomic ions. Maybe we'll get to play a little bit more Yahtzee this afternoon, or second period, to just solidify those in our brains. Alright. I need you to write this down. This is the periodic law. Periodic law says elements are periodic functions of their atomic number. And what that means is there are repeated patterns on the periodic table that happen over and over again, and that all of the elements on the periodic table are arranged according to their atomic number. They used to be arranged according to their atomic mass, but then they got smart and they said, hey, something funky goes on down here at the end of the periodic table, so we will just arrange them according to their atomic number. And there was a scientist, he was a Russian scientist, we're going to watch a short video on him, who's the guy who arrange them according to their atomic number. Good morning, Caleb. How are you? Okay, we all got this? I'm holding. Alright. Dmitri Mendeleev. This guy. He's a scientist dude. Like, we had all of the other scientist dudes. Now we got Dmitri Mendeleev. And he noticed that elements... First of all, he went to bed one night. And he was laying in bed where you do your best thinking. And he said, hey, some of these elements have similar properties to each other. And he noticed that he could arrange them on a table according to these properties. He arranged them according to atomic mass, which we know today is not the way that it was done. But because Dmitri Mendeleev did something very, very, very special, and that special thing that he did was he said, I'm going to arrange these elements, and I'm going to predict that there is an element out there that would fit in this spot on the periodic table. That element happened to be gallium. And he didn't call it gallium, he called it aluminum. But it was gallium, and he said, I have this table, and there's a spot right here on the table that's missing. But someday, someone is going to discover this. And sure enough, they discovered that element. And that's why he's given credit for being the father of the periodic table, Dmitri Mendeleev. I'll put it back in a second. Hold on. Because there's a lots of bits and pieces on the periodic table that we have to actually start looking at. We're going to start with the basics. Okay, I want you to find that dark staircase line. Yours is in black, that runs right to the left of boron all the way down between polonium and astatine. You're going to see a dark line. Do you see that? Okay. That splits the periodic table in quote-unquote half. I know it doesn't look like half, but we're going to say the left half and the right half. Okay? The elements that are located on the left of that line are considered our metals. So anything to the left of that line. Now there is an exception. Hydrogen is not a metal. Hydrogen is a non-metal. It's over there for another reason. But all of these guys, most of the elements on the periodic table located on the left side are our metals. Okay? Which leaves us for the right side, or the other half, and I have them highlighted in pink here. These are going to be our non-metals. And right along the staircase, I have them highlighted in yellow, are what we call semi-metals or metalloids. Sometimes you're going to see them called semi-metals. They're the ones that are right between the metals and the non-metals. Now, if somebody's going to ask me about down here, these guys are still metals. Because they belong right here in this little space in between lanthanum and hafnium and actinium and rutherfordium. Right there. These guys belong. So anything to the left of this staircase we're going to consider a metal. Anything to the right of the staircase we're going to call that a non-metal and hydrogen. And anything that's touching the staircase, we call those semi-metals or metalloids. Now the semi-metals or metalloids include everything that's sitting on top of the stairs and germanium and antimony. Aluminum is a true metal. You have aluminum pie pan, aluminum fork, aluminum whatever. It is a true metal. And the same thing with polonium. We are going to consider it a true metal. And the reason why we're going to do that is because some reference tables or some will say that this could be a metalloid as well. But for our purposes, we're going to consider that a metal. Any questions on metals, non-metals, and metalloids and where they're located? Pretty easy. Okay, where or what classifies something as a metal? What makes something a metal? What kind of properties, what kind of physical properties would a metal have?
Probably a specific melting temperature.
Okay, it's going to have a specific melting temperature. You think it's going to be high or low?
Pretty high.
It's going to be pretty high. Okay, some of them do, some of them don't. Okay, gallium, which is a metal, right here, has a very low melting point. It melts in your hand. I actually have some gallium somewhere, if I could find it. Sometimes I get my hands on some elements and then they disappear because I'll see if I can find it for you one day. Whereas some of these metals over here have higher melting points. Okay? So generally metals are going to have higher melting points, but not all of them. What else can we use to classify metals? A physical property of a metal. Perfect. It's shiny. Now in chemistry we don't call it shiny, we call it has luster, but it's the same thing. It's shiny. Metals are shiny. What else do we know about metals? You're thinking too hard. It's shiny. What else does it do? Some of them, like iron, can be magnetic. Okay? Some of them can be magnetic, not all of them.
Conducting electricity.
It conducts electricity. You do not want to stick a metal fork in an electric socket because you're going to get the shock of your life. It will conduct electricity. Alright, so here's a list of some of the properties of metals. Let's write them down. Luster means that it's shiny. Ductile. Have you ever heard of the word ductile? Maybe. It means it can be drawn into wires. It can be made into a wire. When I say drawn, what I mean is, excuse me for a second, they can heat it up and they can pull it really fast and you're going to get a nice thin wire out of it. It's malleable. That means it's shapeable. You can make metals into any shape you want. It's also bendable. You can hit it with something and it can flatten out and become a sheet, like a sheet of aluminum foil, or a sheet of copper, or a sheet of sheet metal. Right? That's where it's coming from. That fancy word is malleable. Alright. It conducts electricity. Does anybody know why it will conduct electricity? By the end of this unit / the end of next unit, you will know why. But metals tend to lose their electrons very easily. They become positively charged ions. Well, electricity is just the movement of electrons. So if the metal is going to lose its electrons very easily, those electrons travel to other atoms. Remember, I kind of started that the other day when I showed you an electron moving from sodium to chlorine. Well, metals can also shift their electrons between other metals. And because they're able to lose those electrons very easily, they can conduct electricity. Because electricity is nothing more than moving electrons. That's what it is. And we can move them right along a wire into whatever it is that you want to power. Dylan, you alive?
Mm-hmm.
Okay. They're also good conductors of heat. When you have a metal object of any kind and you put it near heat, those atoms move very quickly and they will absorb the heat from whatever heat source you have, and they will conduct that heat. That's why you have a metal spoon in your soup gets very hot very quickly. They'll also lose their heat very quickly. So they will conduct heat and electricity. And they're going to have high melting points, which is what Ducky said, okay? And they're also going to have high boiling points. Now, not all of them, but a lot of them, okay? They're going to have these high melting points. Any questions on the physical properties of a metal? Do you have them all written down? Okay, because they do ask those. All right, now let's go to the nonmetals. Nonmetals are dull. That doesn't mean they're boring. That means when you look at them, they look flat, not shiny. They are brittle, like plastic. If you try to bend it, it's not going to be able to be shaped. It's going to crack, right? Malleable means I can take a metal. If you ever did like metal wire sculptures, you can bend that metal, or you could take the aluminum foil and make it into a swan. Whereas the plastic, if I handed you a piece of plastic, it's not going to bend. It's going to be brittle, not bendable. Nonmetals do not conduct heat or electricity. There are a few exceptions to that. There's always exceptions. But for the most part, they are poor conductors. Think about it this way. If I took a piece of carbon, I'm going to simplify it, even though this is not really 100% true. But let's think of the carbon as a piece of wood. If I stuck that wood into an electric socket, would I get electrocuted? No. Okay. Rubber is it's not an element, but it's an insulator. It's not going to conduct electricity. So think of these nonmetals as poor conductors. They don't allow electricity to pass through them. So when I was in Florida last week, there was some really bad lightning storm, and we were driving north on I-75, and I swear, I was driving. I swear I saw lightning strike the road right next to us. And I think it might have been Mrs. Verdisco. I don't remember. She's like, oh my gosh. I'm like, don't worry about it. We have rubber tires. And that insulates us from the ground, so we would be fine as long as we stayed in the car. Think of poor conductors as being these insulators. Alright, and now you have low melting points and low boiling points. That means that they are going to melt and boil at extremely low temperatures. If you melt or boil at a low temperature, you're going to turn into a liquid very easily. You might even turn into a gas. Oxygen, look on your periodic tables. See where oxygen is? It's a nonmetal. It's a gas at room temperature. It's a gas at room temperature because at room temperature you've already reached its melting point and its boiling point. It has turned into a gas already. So its boiling and melting points are going to be very low. Take your reference tables out and flip to table S, which is the one right after the periodic table. Okay. On table S, we've got some properties. Look at oxygen. Oxygen's boiling point is 90 degrees Kelvin. That's pretty low. Let's take a little side trip here. How do we measure temperature? Degrees what? Celsius, Fahrenheit, or Kelvin. Okay? We are not ever in this class going to talk about Fahrenheit. We're only going to talk about Celsius. Okay? So, let's take these two and move them over here. At what temperature does water freeze in Celsius? 0 degrees Celsius. This is freezing. And at what temperature will it boil? 100. Good. If we were doing Fahrenheit, it would be 32 and 212, which are very ugly numbers. For some reason, we do that in the United States. We talk about Fahrenheit, but for the rest of the world, they use Celsius. Now, Kelvin. Do you know what temperature water freezes in Kelvin? 273. Okay, so here's how he knew this. Okay, I know, like mind blown. Flip to the back of your reference table. See where it says temperature, way down at the bottom? Okay. In order to go from Celsius to Kelvin, we have to add 273 to the Celsius. So 0 plus 273 gives you 273 Kelvin. Now, what about boiling? And what temperature put your hand down. What temperature would water boil in Kelvin? All right, we'll clue you in. Go ahead, Adrian. 3. Okay, so Celsius plus 273 is going to equal Kelvin. If you have 100 degrees Celsius, hold on a second, and we add 273 to it, 373 Kelvin. Now, what makes Kelvin so awesome? There are no negative Kelvin values. It's only going to be positive. What? Okay. The lowest number you can get in Kelvin temperature is 0 degrees Kelvin. Well, I shouldn't say degrees, sorry. 0 Kelvin. That is absolute zero. So absolute zero is 0 Kelvin. That's as low as it can go. We have never reached absolute zero. It's the absence of all heat. That means the atoms stop moving entirely. Because when we are measuring temperature, we are actually not measuring heat. We are actually measuring how quickly the atoms are moving. And when you get to 0, the atoms have stopped moving entirely. Okay, so if I gave you any other temperature, let's say I had 55 degrees Celsius, and I want to know what that is in Kelvin. It's a bad K. How would you figure that out? Celsius plus 273 equals Kelvin. 55 plus 273 equals Kelvin. 8, 12, 328. Did I do my math right? Mm-hmm. 328 Kelvin. Now let's go the other way. Let's take 435 Kelvin, and what is that in Celsius? $162. Okay, that's as easy as it gets. Every time you move 1 degree Celsius, you move 1 Kelvin. So what that means is if I go from 1 degree Celsius, which is 274 Kelvin, if I go to 2 degrees Celsius, I go to 275 Kelvin. See how the difference with this is only 1 degree, and over here is 1 degree? It's just sliding the scale so that there's no negative numbers. That's all it is. Okay? Because when we do gas laws, you cannot have negative values. It's going to have to be positive values. All right, I got a little off track here. Write this down. Temperature is equal to the average kinetic energy. Kinetic means movement. So when I talk about temperature, I'm actually talking about the movement of the atoms within the substance we are talking about. You are measuring how quickly they are moving. All right, take your break. You done good.